Hello everyone, this is lecture number 2 and we are going to discuss about N-channel JFET. As we discussed in our previous lecture that FET is divided into two parts, N-channel JFET and P-channel JFET. So in this lecture we are going to briefly about N-channel JFET. Now let us start with FET types or JFET types. There are two different types of JFETs. Number 1 N-channel JFET and number 2 P-channel JFET. So in this lecture we are going to discuss about only N-channel JFET. So let's start with its symbol. So here we can see this is the JFET symbol. N-channel and P-channel both are available here. So in this particular topic we are going to discuss about only N-channel JFET. This is already discussed in our lecture number 1, which is based on FET introduction and its types. This is similar to that lecture. So here we can see drain, gate and source. There are three different types of terminals in FET, or we can say UJT. Whereas in BJT, bipolar junction transistor, there are three terminals which are base, collector and emitter. But here drain, gate and source are the terminals for the FET. Now terminal names and its region. Actually this FET is look like this construction. Here we can see this is the FET construction. There are three different types of terminals: drain above, in between there is a gate and below we can see there is source. So now gate is connected to the P-type material at this end and that end. So it is gate terminal. Whereas here we can see drain and source are connected to the N-type material. Now here we can see N-type material. Between the N-type material and P-type material there is a depletion region. So we are going to discuss about this depletion region and how current flow and how current reduce through this depletion region is our main theory in this topic. So let us discuss about N-channel JFET construction along with its biasing. Here we can see this is the planar construction, diffusion of P case, and here we can see this is the N-channel JFET construction along with its biasing techniques. Now this is the construction in which we are going to biasing this terminal like this. Obviously we have to connect two batteries because there are three different types of terminal. It is similar to the BJT. Right, so here we can see gate and source, which is connected with the VGS, which is known as gate to source voltage, and that is our main input voltage from this construction. Here at this end, here we can see this is the VDS. VDS, that means it is the voltage difference between drain to source. That means this battery is connected in between drain and source. So it is known as VDS and this is our output voltage. And current flow through this direction in output side is known as output current, which is known as ID, or we can say drain current. So here we have to control this drain current ID through this VGS. That's why it is called as voltage control device. So remember this thing, why FET is called as voltage control device, because it control the current, it control the output current ID, drain current, through VGS, through voltage voltage at gate to source terminal. So now let us discuss about its brief working principle. Here we can see this is the N-channel Jfet working and its principle of operation. So we are going to discuss it in three different parts, or we can say cases. Case number one, first there is VGS is equal to 0, or we can say no VGS is applied in this construction. Then what happened? We have to measure this thing. Case number two, small negative VGS is applied. Remember this thing, here we have to apply negative VGS because it should be in reverse bias, and then we will get depletion region increased in that particular construction. And last, case number three, more negative VGS is applied. So we have to conclude these three different types of cases in this theory. So let's start with case number one. So case number one, when no VGS is applied, that means VGS is equal to 0. Practically that means VGS, that means gate to source voltage, basically shorted. So that means there is VGS is equal to 0, no VGS. If there is no VGS, that means there is no depletion region built in N-type and P-type material. And that means the flow of ID is maximum at this VGS is equal to 0. Here we can see it is working because there is no depletion region. So channel width is larger. Here we can see it is clearly visible, channel width is larger, so the flow of current, the flow of drain current is maximum. So it is also known as maximum drain current at VGS is equal to 0. Here we can see no VGS is applied, so that means it is short circuited, small depletion region exists, channel width is available for current flow, and maximum current will flow when no bias is applied. So here we can see this is the channel is available here. Now let us discuss about case number 2. Case number 2, that means when small VGS, small negative VGS is applied at this terminal gate to source voltage. Now here remember this thing, VGS should be in reverse biased. So we are going to connect it with reverse bias. And how it becomes reverse bias? Clearly visible here, it is P-type material which is directly connected to the battery's negative terminal. Now remember this thing, P-type and battery's negative, that means N, P and that is N, both are dissimilar, that means it is in reverse bias. So here we should connect it in reverse bias condition. Now if we applied small negative voltage, then what happened? If we applied small negative voltage at VGS, that means here the depletion region width is penetrated more into the N channel. If it penetrated more, that means it is the obstacle for the flow of drain current. That means your drain current flow will be reduced whenever your depletion region width is increased. So here we can see depletion region will be penetrated more in the channel. Channel width will be reduced as depletion region will be increased. ID, that means drain current will be decreased as reverse bias negative VGS is increased. So here we can see this is the channel width is reduced. Now let us discuss about case number 3. When large VGS is applied, that means if we applied more VGS here, so your depletion region of other side is touch to the depletion region of front side. That means there is no gap remains between the N channel. It means if you increase your VGS in negative side, then the flow of ID becomes reduced. So here we can see VGS is applied as shown in figure. Depression region will be penetrated more and more into the channel, and the channel width becomes decreased. So ID drain current will be decreased to 0. That means ID is equal to 0 at VGS is more negative. That means no current can flow through this channel. So here we can see channel is totally blocked, because here we can see depression region is touches together. So final, this is the N-channel JFET working 3 cases together. Here we can see these are the 3 cases. First we can see here case number 1, then case number 2, and last case number 3. So in these 3 cases we can justify this N-channel JFET. Basically it is work like a dam's gate. If the water can flow that particular dam's gate, that means if your gate is initially open, that means your flow of water is initially increased. Whenever your gate fully open, that means the flow of water maximum. Here we can see in case number 1, if your dam's gate is totally open, that means flow of current is maximum. And in this case we can say the flow of water is maximum. If you close this dam's gate, this is the case number 2. Initially we starting this gate is closed. At this time the flow of waters is reduced. Similarly here in case number 2 we have seen that if your depression region width is increased, the flow of ID becomes reduced. And finally the gate is totally closed. That means the flow of water stops. Here it is happening in case number 3. If depression region touches together, that means it stops the flow of drain current. So we can give example of this for N-channel JFET. So that's all for today's lecture. Till then, keep reading, keep learning. See you soon in next coming lecture. Thank you.